Okay, we talked about general exhaust systems, different types of exhaust systems. One of the things that we're not going to cover is we're not going to cover dilution exhaust. We're just going to cover, since we skipped that part, we moved that to the second half of the semester when we're going to be dealing with those kinds of systems, especially since HVAC system and HVAC system is, in a sense, a dilution exhaust, a dilution control system as well. One of the things, among the other things that are going to be on the exam, are things that involve questions involving recognizing what a hazard might be, what kind of hazards it might have, whether they're particulate material, whether they're vapors, fumes, so on and so forth, biological hazards. Here's some examples of them. I'm going to go through these really quickly because there's a lot of them. Some operations have special considerations. For instance, grinding, you have special kind of enclosed hoods and so on and so forth. Automotive spray booths, so on and so forth. We haven't discussed lab hoods. I think we really got to squeeze, before the end of the semester, squeeze in some stuff on lab hoods. We have certain goals that we're trying to accomplish here, mostly involve protecting workers. You guys remember the levels of administrative levels OSHA has for dealing with hazards? Remember what the first level is? What do you do with the first level? What's the first thing you try and do when you have a hazard? Eliminate the hazard. Excellent. What's the second thing you do? Skip one. Substitution. Exactly. Right. There you go. Substitution. Right, exactly. Substitute another material that's less hazardous, let's say, or a process that's less hazardous. And the idea of these layers is that if you eliminate it, then you have solved the problem. You can't have something go wrong if you eliminate it. If you substitute for it, you've eliminated it in a sense again. What's the third level? Engineering, right? There's the engineering. You engineer out the hazard, or you minimize the hazard by engineering. What's the fourth level? Administrative, yeah, okay, that's administrative is the next level. In other words, we're going to train you and make sure that you know what the hazard is and how to avoid it and so on and so forth. We're going to make rules that help you avoid the hazard. Not so good, right? Not as good as engineering, not as good as elimination, because not everybody obeys the rules. What's the final level of protection? Right, personal protective equipment. So what we're doing with these hoods, right? Well, we're not eliminating it in the sense that we're taking away the material that's a hazard. We're not substituting for it because it's still using the same solvent or material or particulate matter or something like that. But this is an engineering control, right? So when we design a hood, we're designing an engineering control. Okay, so these are the goals of engineering controls. Okay, so all you guys take industrial hygiene, the basic industrial hygiene course? Okay, yeah, okay. Yeah, that's kind of a prerequisite for this, I would guess, right? Maybe. I guess they're not that rigorous about that stuff, right? Okay. So again, we reviewed the basic components of a ventilation system. You got a hood or some sort of device to capture the contaminant. You got ductwork. You have an air cleaner. Almost always have an air cleaner of some sort of or other, because if no other reason, you got to protect the fan or the other equipment, or eliminate a hazard that you might be discharging outside. You got the fan, which you need as an energy source to actually keep this whole thing operating, and you have an exhaust stack, right? Any one of these components is missing, you don't have a system, right? Without an exhaust stack, you have nowhere to discharge it. Without the ductwork, you don't have anything. So this is like the minimum that you would need for an exhaust system. Okay, so components: the hood, the duct, the fan, air cleaner. Sometimes they're mostly mechanical filters. Often there may be activated charcoal. They may be I've seen air washers, water type spray air washers in some systems. Exhaust stack or discharge. Anybody know any specific rules about exhaust stacks from these systems? Okay, New York City has a building code. What do they say about chimneys and exhaust stacks? Got to be what height? What if you're within 50 feet of any part of the building? How high above that the building you have to be? 10 feet. Right. Got to be 10 feet above any structure within 50 feet. Okay. Of course, from our perspective, we got some other rules besides that. We want to make sure we're not in an area with this fresh air intake, openable windows, that kind of stuff, because you can always have downdrafts. right? Anybody, any guys work with cooling towers ever? Right? Cool. Yeah, there you go, Legionella samples. But cooling towers, the way that they work is that you suck air in from the sides and you discharge air out the top. And that air is being blown against a spray of water because you want to cool that water by evaporation. So you want a fine spray of water and you want a lot of air so you maximize the surface contact between them and you cool that water so you can use it to cool the air conditioning system. Right? So what happens is you're sucking in air alongside of these towers. If you have a smokestack nearby, even if you're meeting the rules, 10 feet above and so on and so forth, and 50 feet or within 50 feet, you can get a downdraft. You can get a lot of this stuff sucked back down. I think if you if you look on some of the PowerPoints, particularly the Jeff Burton PowerPoints, he has a couple of situations there where he shows situations where you might get downdrafts. Remember, he doesn't like rain caps at all. Did you catch that in his presentation? Hates rain. I don't know what he does about the rain because without a rain cap, it's raining in and you're getting the water inside the exhaust duct when it's not running and stuff like that. But he doesn't like them because they number one, they interfere with the flow of air coming out of the exhaust system, so they're one more source of loss of energy. And number two, they direct the exhaust downwards. You know, so if it's particulate, you're just turning it around and just dropping it down into the onto the roof. Okay, some components. This is an induct. It happens to be an induct axial blade. A lot of times you'll see these squirrel cage kind of. Yes. Oh, you know, I was trying to get rid of that, but for some reason it has a different format than the one I have here on my computer, and I can't get it to go away. I don't want to leave the meeting. No, see, it closes it. I don't know why that's doing that. Yeah, I tried that before. I think it just changes the. It just puts it into a window. It just puts the rest of the screen into a window. And oh, there it goes. Just let me drag it.
I'm not sure.
See, mine has a little arrow on it, which is usually what shows up to minimize these things. Good, that should do it. Okay, back to work. Centrifugal separators, you see quite a bit of those because they, hi, how you doing? They impart a lower, they're less aggressive in terms of like blocking the flow of air. You get a lower static pressure drop across centrifugal separators very frequently. They only work very well for relatively heavy particles. The way that they work is they spin the air, and the larger particles get thrown to the outside, and they drop down to the bottom where they can be discharged. Anybody know in the lab when you took the environmental lab where you use a centrifugal separator? A little bit smaller than this one. Well, impingers, yeah, but you used it. Remember, you did your particulate sampling, right? That little device that you put on there, that cyclone, was a centrifugal separator. Okay, it spins the larger particles get spun out and they drop into the bottom. So that literally, if you have exactly the right velocity of air going into that thing, then you can predict that particles over a certain size are going to get trapped before they go to your filter and get counted as part of your particulate matter, your gravimetric analysis. So you can predict, oh, well, all I'm going to get with this device on here, all I'm going to get going onto that filter is going to be the particles smaller than, say, 10 microns or 4 microns, or whatever it happens to be designed for. Transitions, flexible duct. Well, what's the issue with flexible duct? Why don't we like flexible duct? Right? I'm sure that there might be a question about that. Well, first of all, as far as ductwork is concerned, the different forms of ductwork, what factors are we looking for in ductwork that affects the performance in the hood, performance in the exhaust system, right? Friction, right? And how was that measured? There was a factor that was in the formula. Remember what that was? That was R, right? The roughness factor, right? And the flex duct has the highest roughness factor of a lot of different types of duct, not to mention the fact that if you can imagine, a lot of times in practice, it's not really straight. It has a lot of bends in it, turns, kinks even, in practice. So it doesn't work very well. Blast gates, what do we use blast gates for? Balancing, right. Do we like to balance exhaust systems? Not if we can't, not if we can help it. We don't want blast gates because blast gates are used to restrict the flow so that we can balance the amount of air that goes to one location and goes to another location, or control the rate that air goes through, the volume of air that goes through there per minute. Okay, the problem with that is that introduces a lot of turbulence, and it reintroduces a big pressure loss, a big energy loss. Okay, we don't want that. We want a system that's balanced, so that's designed so it's balanced so that we don't need blast gates. So that as soon as you turn the switch on, even just the ductwork, the sizing and lengths of the ductwork balance the entire system. So you don't need to control the amount of air going from one hood or another hood or through the whole system. Now, in the system we have downstairs, there is a blast gate. And there's a blast gate on there so that as we do experiments with it, we can control the amount of air that we're pulling through there, so we can actually do a few experiments with like of high flow rates and lower flow rates and so on and so forth. But in a real exhaust system, we want to avoid them as much as possible. If we don't mind the cost of energy, if we don't really want to spend a lot of time designing a system, we can install blast gates and just oversize the fan and the ductwork and everything else, and then just control it with a blast gate. In air conditioning systems, we don't see blast gates. What do we see in an air conditioning system instead of a blast gate? Instead of this thing that just dropped. In air conditioning systems, the only thing that you'll see that looks like a blast gate is something called a fire damper. A lot of times in air conditioning ductwork, they will have a damper, a blast gate, that's hung up and held with a fusible plug, a little piece of metal that melts at a low temperature. So if there's a fire, that blast gate, that little plug will melt away, and that blast gate will drop down and block the flow of air. And that's literally just like a blast gate, just a piece of heavy sheet metal that drops down, blocks the flow of air. But we don't usually see blast gates in HVAC systems for adjustment. We basically see these butterfly valves, right? They're like round duct. When they're closed, they completely fill the ductwork, and you can gradually open and close them. We can afford to see them in HVAC systems because in HVAC systems, the flow rate of air going through the ductwork is much lower. If we use them in an exhaust system, that you wouldn't be able to hold them in position. You're moving air so rapidly through most exhaust systems that they would just kind of blow them out of the way. It would be hard to keep them in position. So you see on local exhaust systems, you see blast gates. On HVAC systems, you usually see these butterfly valves, these control valves. You guys know what I'm talking about there? Have you seen them? Right? I'll come up with a picture one of these days. Canopy hoods. Okay, where do you use a canopy hood? What kind of situation? Well, you want to use it where the contaminant is going to go up into the hood. And where's that going to happen mostly? When you have a heated tank, right? Okay. Yeah. During the week, when you read these questions on the exam, I hope you're going to have an easier time with them, you know? I mean, some of these are obvious, right?
When you have a what?
Yeah, heated. When you have a contaminant that's in a heated, that's heated, for instance, because the warm air is going to rise. So a canopy hood, if your hood is above the process, you're putting it above the process because you expect the contaminant to go that direction, and you want to control it from escaping somewhere else.
From where I've seen them in research settings, they're used for anesthesia, for capturing anesthetic gases.
Oh, no kidding. Why? Because they're lighter than air?
Correct.
Oh, okay, there you go. There's another reason for it to rise, yeah. Yeah.
And as opposed to having it in a big chemical hood where the researcher can't like necessarily stick their head and have that close access, you know, you get one of these canopy hoods with a nice little cone and you bring it close to the animal. And
right.
You have a very high flow rate and you're pulling the anesthesia away
from
you, but then you can quickly work and, you know, manipulate if you're extracting an organ or something.
Right. Although that's movable, right? That you bring right up against the work and so on and so forth. Yeah. So you're not really relying on it completely to rise, but you're bringing it also close. Most canopy hoods you really can't. There's fixed. You really can't drop them down.
This is the arm.
Yeah, yeah. And where might you see a canopy hood? On every block in the city.
Bodega.
Huh?
Bodega.
Yeah. Well, maybe not so much a bodega, but a restaurant. right? Anywhere with a kitchen, right? It's going to have a canopy hood, right? Because exactly that kind of situation. You're cooking, you're producing grease fumes and so on and so forth. They're going to get pulled up into the kitchen hood. Okay. There's going to be some questions on physical characteristics of air, density and standard temperature and pressure, so on and so forth. There'll be a few questions on there about that. You have the references in the book, so it's not something that I think you're going to find particularly challenging, but you'll really just have to look it up and figure out how to use it. You'll have some questions that may involve the gas laws. Okay, and for instance, it may involve, this one includes density and so on and so forth. To a large extent, we've been ignoring the effects of temperature and density, right? We've been like just considering standard temperature and pressure. You might have a question or two that may ask you to do a conversion here or there. That'll ask you to use the density factor possibly, but this is something you can go into the reference material and you can look up the formula and you should be able to figure it out. I don't think you'll find that too challenging. Pressure and volume, you know that if you double the pressure, what happens to the volume? Double the pressure, volume, right, goes down, right? It's half the volume, right? Twice the pressure, half the volume. Okay, now keep in mind that that's absolute pressures and same thing with temperatures. Temperature goes up, volume goes up. Temperature goes up, you keep the volume the same, the pressure goes up, right? So there's our relationship there. So now keep in mind that when you're dealing with pressure and temperature, you're dealing with the absolute values of pressure and temperature, and not what's pressure that's on a gauge or a manometer. You're dealing with the atmospheric, everything from zero atmospheric pressure zero atmospheric pressure, not gauge pressure, on up. So zero pressure on a gauge is 14.7 psi absolute. Okay, so and temperature is going to be either Kelvin, 0 Kelvin, or 0. I don't know what Fahrenheit, Röntgen or something, or what do they use these days for zero? What's that?
For temperature?
Yeah, 0 Fahrenheit. I mean absolute 0 Fahrenheit.
I was looking at that example. You use Fahrenheit in your equation. Should we have put the right?
Yeah, that's not right. Yeah, that's not right. That's why I'm bringing it up. I don't know. Actually, this is not my slide. I won't accuse anybody of having made that error. But remember, we did that example with the football, right? And we did convert, our temperature and our pressure to absolute. Okay, so next important formula that you're going to come across quite a bit is the relationship between static pressure and velocity pressure. The deal here is that static pressure and velocity pressure are measures basically of energy, right? Static pressure is potential energy. Velocity pressure is kinetic energy. It's actual movement. Okay, just like if we were at Niagara Falls, that water up 500 feet high is full of potential energy. When it comes down, you're exchanging that potential energy for kinetic energy. When it comes down to the bottom, you've lost all that kinetic energy from the top. So it's a trade-off. Static pressure and velocity pressure are a trade-off. If you go through a transition, velocity pressure goes up, right? Let's say you go through a transition where you go through a wide duct to a narrow duct. What happens to the velocity? It goes up, right? What happens to the velocity goes up, the velocity pressure goes up. At the same time, what happens to the static pressure? The static pressure goes down, right? Because you're exchanging the two of them. When you go through a transition, you go from a narrow duct to a wider duct. What happens to the velocity? It slows down. So what happens to the static pressure? It goes up. Okay, so it's a little bit tricky when we deal with it because the static pressure, most of the system that we're most concerned about is on the suction side of the fan. So the static pressures are negative numbers, but they still do the same thing, right? Well, maybe we'll get to an example. We'll actually work through it. The other thing that's a little tricky is because we're on the suction side of the fan, very frequently, if not almost always, the total pressure is going to be a negative number because the static pressure is often higher than the velocity pressure. So total pressure on that side is often a negative number. On the discharge side, total pressure is always going to be a positive number because both the static pressure, pushing out against the ductwork, and the velocity pressure, movement in the air, are both going to be positive numbers. On the suction side, it's the other way. Because the static pressure is going to be always a negative number, the velocity pressure frequently is not as high as the static pressure. Total pressure very frequently is negative. Interestingly enough, you exchange the two of them, basically you're equaling them out. If all things were perfect and frictionless in this system, the static pressure and the velocity pressure would be, they'd be opposite. On the suction side, they'd be opposite numbers, but they'd be the same quantity. Okay, but as we go through each transition, we lose some energy. Okay, so I would try and get familiar with or remember how a manometer works and how a pitot tube works. So in this system, the first device that we see there is measuring velocity pressure, right? And it's measuring velocity. Well, hang on a second. Let's think about that for a second. It's not really measuring velocity. What is that really measuring, that first device? This is another bad slide, right? I'm going to start with the last one because the last one happens to be right? The last one, SP, is actually measuring static pressure, right? It's measuring the pressure at against the side wall of that ductwork. And the reason why we're measuring it there is because static pressure acts the same in every direction. Okay, we don't want to measure into the flow of air or against the flow of air and so on and so forth. We want somewhere where we're not getting influenced by the velocity at which the air is moving, and that's the side. Okay, so that's measuring static pressure. If you imagine blowing up a balloon, that extra pressure that's in that balloon is all static pressure. It's not moving, but it is exerting pressure against the sides of the balloon. And it's the same pressure whether you're in the middle of the balloon, towards the left side of the balloon, to the right. It's always the same pressure. Same thing in the ductwork. That suction pressure, that negative pressure, is acting throughout that duct at that point. Doesn't matter where you are. So now, if I put a tube in there, I'm going to go to the second one. If I put a tube in there, and the air is blowing into that tube, as we are in the middle version of this. Actually, it is right. In the middle version of this, if the air is blowing into that tube, what pressure is blowing into that tube? We have the velocity pressure is blowing in there, right? But we also have the static pressure is also acting on that tube because it acts everywhere in that duct. So the velocity pressure is what sign on the suction side of the ductwork? It's positive. The suction pressure on the before the fan is what? Positive or negative? Negative. So the total pressure when you add them together is actually smaller than just the static, is a smaller quantity than just the static pressure. The total pressure is going to be equal to the velocity pressure plus the static pressure. So now let's see what we have here. So we have 1 inch of water as suction pressure, right? And we measure the total pressure is only 0.3 inches, right? So both of these are negative, aren't they? Because if you look at that fluid, it's being pulled into the ductwork, right? So the reason why the total pressure is not as great a negative number as the static pressure is because the velocity pressure is positive. The flow, the pressure from the velocity is a positive number. So if we look over here, if we look at this, if we want to calculate the velocity pressure, what would, looking at just the first two devices on the right-hand side, what would the velocity pressure be? Well, the total pressure in the formula is 0.3 inches. The velocity pressure, excuse me, the static pressure in the formula is 1 inch. So 0.3 inches is equal to, actually I should say negative. Negative 0.3 inches is equal to negative 1 inch plus, what's the velocity pressure have to be? Negative 0.3 is equal to negative 1 plus, what does that velocity pressure have to be to make that equality?
0.7.
It's got to be a
0.7.
positive number, right? Because
Yes.
you want that -1 to be negative point. It's going to be a plus 0.7. Does that make sense? I see a lot of, I'm going to have to, let me escape this for a second. Let's do it this way. Okay, because this is kind of fundamental. Okay. Okay, so now total pressure is equal to the velocity pressure plus the static pressure. I changed the order, but it doesn't matter. What was the total pressure again? It was negative 0.3. And that's equal to the velocity pressure, which we don't know, right? But we do know the static pressure, and that was -1, right? So what does the velocity pressure have to be? Going to move +1, right? What's the velocity pressure equal to? 0.7 plus 0.7, right? The velocity pressure is a positive number, right? So if I go back to this diagram here, okay, if I go back to this diagram, well, what's happening here is the static pressure is -1 inch. It's being sucked in by 1 inch. It's sucking hard enough to pull the column of water up 1 inch. Now, the total pressure, this is measuring that -1 inch of water. It's being sucked up -1 inch, but at the same time, the air movement in this direction is pushing it back down. But it's not pushing it back down completely. It's pushing it back down so that it's still a -0.3 inches, right? So how high must that pressure that's pushing it down be? It must be a plus 0.7. Okay. Okay. You have to look at me so I feel comfortable that you're actually catching this. Make sense? Right? Now, the way a pitot tube works is that it does both at the same time. This side is measuring the static pressure, right? This side is measuring the total pressure, right? So the difference between the two of them is what? The velocity pressure, right? This is measuring total pressure because it's in the ductwork facing in the direction of the flow of air. So there's two things that are acting on, oops. There's two things, can you see the arrow there that I'm moving? There's two things that are acting on at the point of this pitot tube. Your total pressure, your velocity pressure and your static pressure are pushing in here, right? So that is going to be your total pressure, pushing on this side. On this side, it's being pulled up by your static pressure. So the difference between the two of them, your total pressure and your static pressure, is your velocity pressure. So 0.7 inches is your velocity pressure. So this device measures, if you have it in this configuration, it's measuring the static pressure. If you have it in this configuration, it's measuring the total pressure because it's measuring both. And in this configuration, it's measuring the difference between the two of them, which is the velocity pressure. Okay, so if you see a pitot tube on the exam and you're asked to interpret this, right, you might not see it in this form. You might see it in the form that we used it in the lab. Actually, I have a picture of one later on. And that thing, when we used it in the lab, it went in here, it was a tube, went in here like this. It's a hollow tube inside of a tube. And then it went down to the bottom and had a little T at the bottom. Had a connection at the end here and had a connection in the over here. Well, the tube in the tube was connected down here. So this end was measuring what's coming in the tip, right? This end, and what was that's coming in the tip? Total pressure, right? And what was coming in here? Well, this was measuring, this is the outer tube. There were little holes in here on the sides of this tube. Is that measuring the velocity pressure? No, all it's measuring is the other pressure that's in here, which is the static pressure. This end measures the total pressure. This end measures the static pressure. So when we hooked it up to that angled manometer, right? Remember that? When we hooked it up to that, we hooked up one end to the total pressure, one end to the static pressure. And the difference that we were measuring was the velocity pressure directly. Okay, there's some diagrams of this in the book. And if you're really stuck, then I'm sure I can come up with some other, maybe somebody else's better description of this, maybe somewhere on the internet or something like that. So you can hear it. You can hear it from another voice. Sometimes it helps to hear this stuff in another voice. I think they'll tell you the same thing, but maybe they'll make it a little bit clearer. Okay, so that's one of the things we want to be cognizant of. Now, one of the issues with the velocity of the air moving through the ductwork. Okay, the air moving through the ductwork is affected by friction on the sides of the ductwork. So if we actually moved it, we would not see an absolutely uniform movement of air through the ductwork, right? What we're going to see is that the air closest to the edge is going to be moving slower than the air in the middle of the ductwork. Most of our calculations are based on the average velocity throughout the ductwork. Okay, that's really what we're interested in, is the average velocity throughout the ductwork, and that's where our calculations are we're dealing with our calculations. Static pressure is uninfluenced by position in the ductwork. It's the same everywhere in that part of the ductwork. Okay, important formula: velocity is equal to 4005 times the square root of the velocity pressure. Okay, we're going to use that very frequently because if we know the velocity pressure, then we know the velocity. If we know the velocity, we know the velocity pressure. We can exchange them. What does D stand for? What is the D in there? Density, right? And in the other formula, what is rho? That same thing, except the English, the actual density of the air. D is a density correction factor. Rho is the actual density, pounds per cubic foot or something like that, depending on what unit that you're using. Where D is a density correction factor, where it's the density compared to at the temperature that you're dealing with in the environment that you're dealing with it versus what it is at standard temperature and pressure. For the most part, we're working with the density correction factors equal to 1. We're just using 4005 times the square root of the velocity pressure. At some point in the semester, later on, as we we'll do at least a couple of examples where we're evaluating ductwork where it's in a location that's unusual, elevation or temperature or something like that. So we'll incorporate that so we can use it. For the most part, you're almost always going to be in situations where you're just going to make your assumptions that it's you're dealing with standard temperature and pressure. Okay, so yep, that was a formula. The volume flow rate, another important formula. Okay, the quantity of air, cubic feet per minute, is equal to the velocity times the cross-sectional area. Makes sense, right? You have a 1 foot square duct area, cross-sectional area of the ductwork. If air is moving through at 100 feet per minute, then the quantity of air that you're moving is 100 cubic feet per minute of air. We want to make sure when we do these calculations, we keep the unit straight, because a lot of times you might be getting the cross-sectional area of the ductwork in inches, but you got to convert to square feet from inches and so on. Okay, so now here's we went through a couple of examples where we had remember, since the quantity of air that you're moving through the ductwork doesn't change, right? If you're putting 100 cubic feet per minute into the ductwork, what are you getting out? Getting 100 cubic per minute out. It's not going to pile up there like traffic on the Long Island Expressway. It's going to come out, right? So what happens is if the duct gets wider, larger area, well, then the velocity has to go down. So in each one of these segments, the velocity times the area in one segment is equal to velocity times the area in the next segment is equal to the velocity times the area in the next segment, and so on and so forth. Because the volume of air going through this has always got to be the same. What if the ductwork never changes cross-sectional area? All through the exhaust system, it's always 12. It's always 12-inch diameter ductwork through the entire system. What's the velocity throughout the entire system? It's always the same also, because you're not changing the area, so the velocity is always the same. Most exhaust systems, once you start sending this through ductwork, you're probably not going to see much in the way of transitions unless you have a reason to have a transition, like entering a filter or leaving a filter or something like that, different size ductwork that you need. Or what's an operational location where you might have a transition because it's important that you have that transition in the ductwork to make it perform correctly. Why would you have a transition in ductwork to make it perform properly? There's one really significant example he gives Jeff Burton gives in his presentations. Remember what that was? It's a situation where he has exhaust going up and out of the building and then running across a roof. And when it comes up the roof, makes that turn, he has a reduction in the size of the ductwork as it goes through the horizontal run in the ductwork. And then when it turns back up, it expands again. Anybody remember why he reduced the size of the ductwork on the roof? He wanted higher velocity. Why did he need higher velocity in that horizontal run?
So it would sink back down into the.
Well, in the horizontal run, he wanted it because he didn't care that much. A lot of times what you'll do if you have a vertical run of ductwork and you're dealing with particulate, you'll have a clean out on the bottom. So you're not so concerned about the stuff dropping out because you usually manage that in one way or another. But on the horizontal run, right, if he doesn't maintain the velocity he needs, the transport velocity that he needs, then it'll start to build up in that horizontal run. So what he did was he narrowed that, increased the velocity to make sure that he had the transport velocity that he needed in the horizontal run because he couldn't put a clean out on it because it's going to drop out all along that ductwork. So you'll see that. You'll see a discharge that goes into a horizontal duct that has a transition that gets smaller because you want to keep up the velocity in that horizontal run. Then when he turns vertically, then you can go to a larger ductwork again if you have a clean out on the bottom for the vertical run of ductwork. Okay. The other thing we're interested in capture velocity. Well, there's a couple of velocities we're interested in. One velocity we're interested in is capture velocity. Capture velocity is the velocity of air, the speed that the air has to be moving into the duct at the location that the contaminant's being produced. So if you have a contaminant being produced at this location, and the opening to the duct, the face of the duct is 24 inches away, you want to make sure that at this point, 24 inches in front of that ductwork, that you have sufficient velocity in that air to capture that contaminant and pull it away from the work or keep it from being escaping into the space. Right, so we got capture velocity. The other velocity we were interested in is transport velocity. We have to keep the air moving fast enough through the ductwork to avoid having this, if it's particulate material, having it drop out. Transport velocity less important with a gas or a vape or fume or something like that because very small part, either welding fumes or something like that, very, very tiny particles, almost gas-like or vapors or gases, right? We're not that concerned about transport velocity as much as capture velocity. So when we design these things, we're interested in where the losses are because we have to design them so that we get that performance that we need from the hood. The place where the rubber meets the road, as they say, I don't know, do they still have the commercials where they talk about that, where the rubber meets the road? I think Goodyear used to do that, right? Where the rubber meets the road, the critical spot in this whole system is the hood, right? That's the only thing that matters in terms of protecting the worker is what's going on at the hood. The rest of the system is designed to make the hood operate right. So in order to make the hood operate right, you have to go through the entire system and design it so that you make up for any losses in transitions, elbows, duct friction, fan losses, hood entry, and so on and so forth. The whole reason for the fan is it creates that suction pressure, right? It imparts the energy into this whole thing that keeps things moving. Turbulence, resistance to flow. In the text, he mentions the idea of measuring when flow is laminar and when it's turbulent. Laminar flow, imagine molasses moving very slowly. It all moves at the same rate, moving very slowly, moving down and so on and so forth, or a stream that's moving very slowly, deep. It's relatively deep. If you've ever gone canoeing, the area where the water is very deep is where it's moving very slowly. You have to paddle. Right? Now, when the bottom comes up a little bit and it's shallow, is when you have that smaller cross-sectional area for that water to go through, or the stream narrows or something like that. Now the velocity has to pick up for that water to flow through it. That area is turbulent. You have white water in those areas. The other areas may be moving very slowly. There's very little turbulence. Laminar flow describes flow of a fluid that's almost uniform throughout the fluid, right? And turbulent flow is when you have more and more mixing or friction or changes in direction and so on and so forth of the fluid. We rarely, when we design duct systems, even HVAC systems, the velocities you're working with are almost always relatively turbulent flow. There's a number that you can calculate based on the velocity, the density, the velocity and the density of the air that you're working with, how fast it's moving, and the density and the roughness of the material around it, called Reynolds number. Okay, you can calculate that using a formula, and generally, when you have numbers that are under 2,000, Reynolds numbers that are under 2,000, you consider them laminar, basically uniform movement. Anything over 2,000, you start to say is turbulent. What we're dealing with is almost always over 2,000. So I wouldn't worry about it. If a question turns up on the exam, you may come across it. Here's the formula, the density, the diameter of the ductwork, the velocity, and the viscosity ties into this too. Molasses is going to be different than air and so on. So you would need these various factors in order. You have to be given a lot of this information to calculate the Reynolds number. Okay, and he does an example here, and in fact, he determines in this particular ductwork the Reynolds number is 12,000. So, from a practical matter, we don't care about the Reynolds number because it's always going to be turbulent. But if it comes up, you know how to find it. Okay, and it is in the industrial ventilation workbook. Roughness of the surface adds to the resistance to airflow. We know that as a R, our roughness factor. So if we're dealing with PVC pipe or stainless steel ductwork or galvanized ductwork, look at those numbers for the roughness factor. Okay, those numbers are very tiny numbers because they're relatively smooth surface. They impart relatively little friction as the air moves through it. But as we go to other materials, concrete, wood, wallboard, and so on and so on. Do they have wallboard on here? Cast iron, ordinary concrete, but I don't see it. I see a lot of ductwork in residential units that uses wallboard. They put together wallboard, put a register on it to use it as ductwork. Not the most ideal situation, but you do see it quite a bit. I don't see it here. But I would say probably that the closest thing to that would be maybe smooth cement, probably similar to wallboard. Okay, so a local exhaust system losses. These transitions, these various devices are the things that add to these losses. First big loss you have is at the hood itself. Air movement is very turbulent at the hood. Directly downstream of the hood, where it connects to the ductwork, there's an area of specifically large loss, which is an area where the air actually pulls away from the ductwork and contracts as it enters the ductwork. Anybody know what that's called? Right? It's contracting, right? And imagine that the ductwork looks like kind of like a vein, like blood flowing, a vein. Remember, Latin term, vena contracta, ring a bell? Vein contraction. Okay, well, I think we'll have an illustration of that. But there's an area of particular turbulence and energy loss right where you enter the ductwork, where you first enter the ductwork, because the air contracts away from the, you get eddies and the air contracts away from the ductwork. Because it's so turbulent right where it enters the ductwork, goes from the hood into the ductwork, where do we measure the static pressure for the hood? Remember? Yes. Yeah, how many?
A certain number of lengths away from
Yeah, 4 to 6 duct diameters from the hood. Usually you're getting away from that area even a couple of duct diameters down. But to be safe, we measured 4 to 6 duct diameters down from the hood. Why are we interested in the static pressure at that point? The static pressure tells us the potential energy. That tells us how much static pressure we have there, tells us how the hood performs, right? We can look up in references, we can look up what static pressure that we need at that point in order for that hood to generate a certain capture velocity. Remember those formulas that we have on, I think it was chart 11? All of those formulas have a couple of factors. They have velocity, right? They have the area, right? And they have the static pressure for the hood, the quantity of air. And once we have that information, we can calculate that static pressure for that hood. So that static pressure for that hood is a way we can measure whether or not where that hood is doing what we need. Very difficult to measure what's going on in the hood, right? Because there's turbulence, there's where you can do it across the face of the hood, a few inches in front of the hood, on this side of the hood, on that side of the hood, a lot of stuff going on there. It's a lot easier to measure the static pressure 4 to 6 diameters up from the hood and say whether or not this hood is performing the way that it's supposed to be, rather than have to make many readings on the hood itself. So that's an important point for us. Once we know we need that static pressure, we can then go to these various other transitions and figure out how much energy am I going to lose at this elbow. Well, I have to make up for that energy. So as I go through this elbow and this selected ductwork, I'm going to lose a certain amount of energy. So in order to have a static pressure of negative 1.2 inches at this point, I have to have a static pressure of negative 1.6 inches just before the filter to make up for the losses between here and the hood static pressure measurement. Okay, that's really where we're doing that's what we're really doing here, is doing these calculations to figure out what this static pressure has to be. Then we know the performance of the air cleaner. We know what the static pressure has to be before the air cleaner to make sure we got 1.6 inches of static pressure before the air cleaner or after, depending on how you look at it. And similarly, what it has to be at the fan itself. Once we get to the discharge side of it, things get a little simpler. Usually that's pretty direct, and there's usually not too much going on there. But we'll get to that eventually when we start to discuss this. Okay, so what's going on? What is actually going on here? What's actually going on here is that starting from the fan itself, the static pressure is a -3. Well, before the filter, it's a negative 1.6. Before all these transitions and the elbows, it's a negative 1.2. And at the hood itself, well, basically outside of the hood is basically zero, the static pressure, right? So what's happening is that the static pressure has to be more and more negative as we come to the fan, okay? Or we're losing static pressure if we work backwards, right? That's really what's happening here. Static pressure outside of this whole system is zero. Static pressure out on the exhaust system is always positive. Notice how it goes down here. Starts at 0.6 inches right outside of the fan, 4 to 6 duct diameters outside of the fan, and then it reduces to 0.5 inches because you've lost energy in this run of ductwork, vertical run of ductwork going up, right? So there's even on the discharge side, you're losing energy. Really, we design the business end of this thing as a suction side, so that's really where we're designing from most of the time. This diagram represents the static pressure. This represents basically the outside of the hood. It's pretty close to zero. It's somewhere between 0 and some small number. It's 0 outside of the hood, and then at the hood itself, at 4 to 6 duct diameters up from the hood static pressure, where we first can practically measure it, is going to be this number here, whatever it happened to be, negative 0.6 or something like that. And here's the static pressure after this number of turns and elbows and so on and so forth. And here's the static pressure before the filter, upstream of the filter. Here's the static pressure. They actually have two filters here. Another filter imparts more static pressure. And here's the static pressure where it has to be at the fan. This particular system, the static pressure at the fan has to be -6 inches of water. That's a lot of static pressure. -6 inches of water to make up for the loss of static pressure across this filter, through the ductwork in order to provide us with that measly little half-inch of static pressure that we need at the hood, right? That's all there to make up for these losses that we have in the system. Okay, a measurement